I'm telling you about latest defects. Ionic crystals have well-defined order of the constituent ions. An ionic crystal which has the same unit cell containing the same lattice points throughout the whole of crystal is known as ideal crystal. However, such ideal crystal exist only at absolute 0 Kelvin temperature. At any temperature above 0 Kelvin, the crystals have some departure from complete ordered arrangement. Any deviation from completely ordered arrangement in a crystal constitutes a disorder or a defect. The crystal may have additional defects due to the presence of some impurities. The term disorder or imperfection is generally used to denote departure from perfectly ordered state of the constituents of the crystals. These imperfections will not only change the properties of the crystals but also give rise to new properties. There are commonly two types of defects in crystals: defects in stoichiometric crystal, defects in non stoichiometric crystals. Defect in stoichiometric crystals. Stoichiometric compounds are those in which the number of positive and negative ions are exactly in the ratios indicated by their chemical formula. For simplicity, we can consider the compounds of the type AB having equal number of A positive and B negative ions. The defects in these types of compounds are called stoichiometric defects. In these compounds, two types of defects are generally observed. These are Schottky defect, Frankel defect. Schottky defect. This defect was discovered by German scientist Schottky in 1930. It arises if some of the atoms or ions are missing from their normal lattice sites. The lattice sites which are unoccupied are called lattice vacancies or holes. Since the crystal is to remain electrically neutral, equal number of cations and anions are missing. The ideal AB crystal is shown in figure 29. The existence of two holes, one due to the missing cation and another due to missing anion, is shown in figure 30. Conditions causing Schottky defect. This type of defect is usually observed in strongly ionic compound having high coordination number and ions, cations and anions of almost similar size. For example, NaCl, KCl, KBr, CSCl ionic solids have Schottky defect. It has been observed that in NaCl there are about 10 raised to power 6 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube there are about 10 raised to power 22 ions, and this means there will be 1 Schottky defect per 10 raised to power 16 ions in NaCl. Because of the presence of large number of vacancies in crystals, its density is markedly lowered. Second, Frankel defect. This defect was discovered by a Russian scientist Frankel in 1926. It arises when an ion is missing from its normal position and occupies an interstitial site between the lattice points. The existence of one hole due to a missing cation from its normal position and occupying an interstitial position is shown in figure 31. In this case also, the crystal remains electrically neutral because of the number of anions and cations remains the same. Conditions causing Frankel defects. This defect generally occurs in compounds in which coordination number is low. Anions are much larger in size than the cations. In pure alkali metal halides, these defects are not very common because the ions cannot get into interstitial position due to their large size. These defects can be found in silver halides such as AgCl, AgBr, AgI, etc. Because of the small size of Ag positive ion, it can go into the interstitial sites. We observe that vacancies or holes are present in the crystals with Schottky as well as Frankel defect, but the former leads to the decrease in overall density of the substance, but the latter does not. In certain ionic solids such as AgBr, both Schottky and Frankel defects occur. Consequences of the Schottky and Frankel defects. Schottky and Frankel defects in crystals lead to some interesting consequences. These are given below. First, because of the presence of these defects, the electrical conductivity of the crystal increases. When an electric field is applied, a nearby ion moves from its lattice site to occupy a hole. This results in creating a new hole and another nearby ion moves into it, and so on. This process continues and a hole thereby moves from one end to another end. Thus, it conducts electricity across the whole of the crystal. Due to the presence of holes in the crystal, its density decreases. However, it may be noted that density decreases only for crystals having Schottky defects. The presence of holes also decreases the lattice energy or stability of the crystal. The presence of too many holes may cause a partial collapse of the lattice. The closeness of similar charges in Frankel defects tends to increase the dielectric constant of the crystal. Differences between Schottky and Frankel defect. Schottky defect, it is produced because of missing atoms or ions from their normal crystal sites. The presence of Schottky defect lowers the density of the crystal. It is generally shown by ionic solids having high coordination number and in which cations and anions are of equal size. Example NaCl, CSCl. Frankel defect. It is produced when some atoms or ions are displaced from their normal sites and occupy interstitial sites. It does not affect the density of the crystal. It is generally exhibited by ionic solids having low coordination number and in which anions are larger in size than cations. Example AgCl, ZnS. B. Defects in non-stoichiometric crystals. The compounds in which the ratio of positive and negative ions present in the compound differ from that required by ideal chemical formula of the compound are called non-stoichiometric compounds. The defects of these compounds are called non-stoichiometric defects. Vanadium oxide, for example, has the formula VOX, where X lies between 0.6 and 1.3. Similarly, iron oxide samples contain more oxygen atoms than iron atoms, while samples of zinc oxide ZnO usually has excess of zinc atoms than oxygen atoms. However, it may be noted that in each case the electrical neutrality of the crystal is maintained. These are of two types depending upon whether positive ions are in excess or negative ions are in excess. These are also known as metal excess defects and metal deficiency defects, respectively. Metal excess defects. In these defects, positive ions are in excess. They may arise due to the following two ways: anion vacancies. In this case, negative ions may be missing from their lattice sites, leaving holes in which the electrons remain entrapped to maintain the electrical neutrality. This is shown in figure 32. Evidently, there is an excess of positive metal ions, although the crystals as a whole is electrically neutral. This type of defect is observed in those crystals which are likely to form Schottky defect. For example, in alkali metal halides, anion vacancies are produced when alkali metal halide crystals are heated in the atmosphere of the alkali metal vapors. The metal atoms get deposited on the surface of the alkali metal halide crystal. Halide ions move into the surface and combine with metal atoms. The electrons thus produced by the ionization of the metal atom diffuse in the crystal and get trapped in the anion vacancies. The electron trapped in anion vacancies are referred to as F centers. These give very interesting properties. For example, the excess of potassium in KCl makes the crystal appear violet. Excess of lithium chloride makes the crystal appear pink. Excess cations occupying interstitial sites. In this case, there are extra positive ions occupying interstitial sites and electrons in another interstitial sites to maintain electrical neutrality. This is shown in figure 33. The defect may be visualized as the loss of non-metal atoms which leave their electrons behind. The excess metal ions occupy interstitial position. This type of defect is found in crystals which are likely to develop Frankel defect. The common example is zinc oxide. Zinc oxide ZnO loses oxygen reversibly at high temperatures and turns yellow in color. The excess Zn2 positive ions are trapped in interstitial sites and equal number of electrons are trapped in neighborhood to balance the electrical charge. These electrons give rise to enhanced electrical conductivity. Consequences of metal excess defects. The crystals with metal excess defects conduct electricity due to the presence of free electrons. However, the conductivity is very low because of the number of defects and therefore the number of free electrons is very small. Because of low conductivity as compared to conductivity of metals, these are called semiconductors. These compounds are also called N-type semiconductors since the current is carried by the electrons in the normal way. The crystal with metal excess defects are generally colored. For example, non-stoichiometric sodium chloride is yellow, non-stoichiometric potassium chloride is violet. Metal deficient defects. These contain less number of positive ions than negative ions. These arise due to two ways: cation vacancies. In some case, the positive ions may be missing from their lattice sites. The extra negative charge may be balanced by a nearby metal ion acquiring two positive charge instead of one. This is shown in figure 34. This type of defect is possible in metals which show variable oxidation state. The common example of compounds having this defect are ferrous oxide, ferrous sulfide, nickel oxide, etc. In case of iron pyrite, FeS, for example, 2 out of 3 ferrous ions in a lattice may be converted into Fe3 positive state, and the third Fe2 positive ion may be missing from its lattice site. Therefore, the crystal contains Fe2 positive and Fe3 positive ions. This gives rise to exchange of electrons from one Fe2 positive ion to Fe3 positive ion, in which Fe2 positive changes to Fe3 positive and Fe3 positive changes to Fe2 positive. As a result, the crystal has metallic luster. Because of the natural color of iron pyrites and metallic luster, some sample of minerals shine like gold and have been nicknamed as fool's gold. Moreover, since there is exchange of electrons, the substance become conductors. Excess anions occupying interstitial site. In this case, the extra anions may be occupying interstitial position. The extra negative charge is balanced by the extra charges. Oxidation of equal number of atoms, higher oxidation states on the adjacent metal ions. This is shown in figure 35. Such type of defect is not common because the negative ions are usually very large and they cannot easily fit into the interstitial size. Consequences of metal deficient defects. Crystals with metal deficient defects are semiconductors. The conductivity is due to the movement of electron from one ion to another. For example, when an electron moves from A positive to it changes into A2 positive. It is also called movement of positive hole, and the substance are called p-type semiconductor. The conductivity of semiconductor is mainly due to the presence of impurities and defects. The semiconductors are very important solid state materials having many important applications in electronics. Semiconductors are important class of compounds which have higher conductivity than insulators and have much lower conductivity than conductors. Thank you.